Yesterday we were talking about superposition theorem and you guys had, some of you had questions about the direction of current, how we determine. So what we did was to take one source at a time. We wanted to take one source at a time. So when we take one source at a time, first thing I did was to take the 10-volt source alone. Okay, so when we took only 10-volt source, we just had the circuit somewhat like this. This is 10 volts and this is 1 ohm and this was 3 ohm and this is also 3 ohm, and we were short circuiting the voltage sources. So I have short circuited the voltage sources here, and we were having 3 and 3 in parallel. That will amount to 1.5. And this is 1 plus 1.5. So when I reduce the circuit, it is going to be somewhat like this. This is 1 ohm, this is 1.5 ohm, and this is 10 volts. Right. So we are going to have the current as 2.5, 10 by 2.5, which is 4 ampere. So 10 by 2.5 will be 4 ampere. So we were having the current to be 4 amperes. So this was 4 ampere current. And that 4 ampere was dividing itself into two halves. Both of them are 3 ohms. So equal current division. So I'm going to have 2 ampere like this. Please note the direction. This is also going to be 2 ampere. Okay. Now when we consider only the 3 volt source. So only 3 volt source is considered. So when we are considering only the 3 volt source, let me draw the circuit once again. So I'm going to have 3 volt source here, which is having 3 ohm resistance in series. Okay, so this is 3 ohm and this is 3 volts. Okay, in fact, let me draw it exactly in series because both of them are going to be together in parallel with the other two resistances. So I should show it as though this is the 3 volt source, and along with that I am having 3 ohm in series, and I'm having on the other hand there is 3 ohm in parallel on one side. The other one, although it is on the other side, this 1 ohm is on the other side, I can still draw it like this. After all, they are all in parallel. So this is going to be 1 ohm. Now I can write this as 3 multiplied by 1 divided by 3 plus 1. So which is 0.75 ohm. So I am going to have essentially 3 volts in series with 3 ohm and 0.75 ohm. Right? And we got this to be 3 divided by 3.75, which was about 0.8 ampere, if I may remember correctly. So this is 0.8 ampere. So I am having 0.8 ampere flowing like this. So if I really look at the original circuit, I am going to have the 0.8 ampere flowing like this. From the positive, it is flowing upward. Please remember, this is what it is. So I should show it as though in the original circuit, this 2 ampere, which was current due to current division from the 10 volt source, it was downward, whereas this 0.8 ampere is upward. That's what I'm trying to emphasize. Okay. Now, if I try to look at what happens to the other voltage source, when I consider the third voltage source, which is 7.5 volt source, so I am going to consider only the 7.5 volt source. So considering the 7.5 volt source only, if I try to consider only that, I am going to have essentially this 7.5 volt source is here, and along with that I'm going to have, what is the resistance? This is going to be 3 ohm, and here is 3 ohm, and here is 1 ohm. So I'm going to have, this is 3 ohm and this is going to be 3 ohm and the next one is going to be 1 ohm. Okay. So now if I try to look at what is the overall current that is going to flow, these two in parallel will again give me 0.75 ohms, 3 by 4 ohm. That is coming in series with this 3 ohms. So 3 plus 0.75, that is going to be 3.75. So I can write this as 7.5 volts divided by 3.75 ohm, which will give me 2 ampere. Okay. Now the total current that is flowing here is 2 ampere. Now out of this, I should say whatever flows here is going to be 1 divided by 4 multiplied by 2 amperes. 1 divided by 4 is because 1 is the other resistance, 3 plus 1 is the denominator, the two resistances put together. So this is going to be 0.5 ampere. So this current is going to be 0.5 ampere. So if you look at the overall current, this was 2 ampere downward, this was 0.8 ampere upward, and this is 0.5 ampere downward. So I'm going to have the overall current through 3 ohm resistance. So I should say current through 3 ohm resistance in the middle branch is going to be 2 plus 0.5 minus 0.8, which is happening to be 1.7 ampere. I hope this gives you clarity in terms of the directions of current, what we were talking about. Is this all right? Okay. So let us now try to look at the next theorem, the next network theorem. So let us try to look at the next theorem, which is actually known as Thevenin's theorem. And another dual to this is Norton's theorem. So this is a very, very important theorem because we keep using this for various electrical networks and circuits. So this theorem statement is somewhat like this. Any complex electrical network which is visualized across a given two nodes can be represented by a voltage source which I specify as VTH, that is Thevenin, in series with a resistance. In this case, I'm talking about resistance because we are only talking about DC circuits with resistance. We are not talking about inductance or capacitance. So I'm calling this as resistance. Otherwise, I should say it is an impedance with a resistance which is RTH. Okay, where VTH is given by the open circuit voltage across the two nodes. So we are talking about visualized across a given two node. So I'm talking about the same two nodes here. So this is the open circuit voltage across the two nodes, and RTH is this V open circuit or V Thevenin divided by ISC, where ISC is the short circuit current flowing through the conductor connecting the two nodes. I'm talking about the same two nodes. So this is generally known as Thevenin's theorem. The Norton's theorem is just a reflection of the same thing or a dual of the same thing in terms of representing, instead of representing this particular network as VTH in series with RTH, the Norton's theorem is going to say it can be represented, again, can be represented by a current source. Within bracket, I would say that is ISC, okay, in parallel with a resistance, which I may call it as RTH. So again, RTH is defined the same way, which is VOC divided by ISC, the open circuit voltage divided by ISC. Let me demonstrate this by an example, then it might become a little clearer. So let me try to demonstrate this by an example, first of all. So let me take one circuit, okay, and then try to reduce it in terms of Thevenin's equivalent. So I would say find the Thevenin's equivalent circuit across AB for the following network. Okay, so you have to find out what is the Thevenin's equivalent circuit for this particular circuit, what we are talking about here. So I'm going to draw the circuit now. So I start with a 1 ampere current source. This is a 1 ampere current source. And I'm going to have an 8 ohm resistance. Then this is 2 ohm resistance. This is a 20 ohm resistance. And I'm going to have a voltage source here, which is a 32 volts source. So this is the circuit. And this node is specified as A. And this node is specified as B. So you are visualizing the circuit from this node AB. And then what is being asked is to give a Thevenin's equivalent circuit for this particular circuit. This entire circuit, you have to get the Thevenin's equivalent. You can do it in different ways, but when you have a current source in parallel with a resistance, you can convert that into voltage source, like what we spoke in yesterday's class. So I can write this as, first of all, a voltage source, which is 8 ohm multiplied by 1 ampere, which will become 8 volts. And this is going to be plus here and minus here, because we are talking about the current is flowing in this way. Okay. Fine.
Ma'am, we have to find the voltage using the resistor which is parallel to it, right?
Yeah.
We have to find the voltage using the resistor which is parallel to it, right?
Exactly. Parallel to it is right now 8 ohm. So 8 ohm multiplied by 1 ampere will give you 8 volts directly.
Ma'am,
So
if there are 2 or 3 which are parallel, you have to find the equivalent resistance.
Yes, exactly. Exactly. So you are going to have this as 8 volts and you will have, of course, this 8 ohm coming in series. This has to come in series. So I should show this resistance as 8 ohm, which is coming in series. Okay. Now after this I have the 2 ohm resistance. So what we have done is this current source in parallel with the resistance we have converted into a voltage source in series with the resistance. The same resistance. That's all we have done. So we have replaced it like this. So this is 8 ohm and this is 8 volts. Okay.
Excuse me,
Now this is, yeah.
Ma'am, why does 8 ohm come in series this time after
The
reducing it?
voltage source which has 8 ohm in series is represented by an equivalent current source in parallel with the same resistance. The current source value you will find out as the voltage source divided by the resistance. Both of them are equivalent. See, if I'm going to have a 8 volt source and 8 ohm resistance, the current that is going to flow out maximum could be only 1 ampere, nothing more than that. So when you represent a voltage source in series with the resistance, that is equivalent to a current source in parallel with the same resistance. The current source value is found out by dividing the voltage source value by the resistance itself. So this is the equivalent conversion criteria that we adopt already always for voltage source to current source conversion and current source to voltage source conversion. Is that clear?
Okay, ma'am. Yes,
Yeah.
ma'am.
ma'am, for
Yeah.
example, if there are 2 or 3 resistors which are parallel to the voltage
Yeah.
to the current source, then we'll
Yeah.
be writing the equivalent voltage. So the resistors also we have to draw all of them separately again in series.
No, no. You once you find the equivalent, then that is good enough, isn't it? If you are going to have, for example, this is the current source, and let us say I have 3 ohm and I have 6 ohm, for example, two of them, and let us say this is going to be a 2 ampere current source, for example. Okay. So I'm going to have 3 multiplied by 6 divided by 3 plus 6, which is 2 ohm. So both of them put together is going to represent a 2 ohm resistance. So 2 multiplied by 2, I'm going to have 4 volts and I'm going to have a 2 ohm resistance. That's it. Fine.
Okay, ma'am. Got it.
As simple
Yes,
as
ma'am.
that.
Got it.
Okay. So let me erase this. So we are going to see that this network is converted into 8 ohm, 2 ohm, and then I'm going to have a 20 ohm here, and I'm going to have a 32 volts source here. Okay. And I hope you guys know that the voltage source can be specified either this way or it can be specified by the battery. Either way is fine. I can specify the 8 volt source, DC source like this, or I can specify the DC source like this. Okay. Okay. So right now this is what is the circuit, and this is going to be A and this is going to be B. Now you can find out what is the kind of current that is flowing through this circuit, right? So the current that is flowing through this circuit is going to be, if I try to look at it, so 8 volts and 32 volts, they are connected in opposing polarity. This is plus and this is minus, whereas here this is plus and this is minus. So if 32 volts is pushing a current, it will push it in the upward direction. Whereas 8 volts is pushing a current, it will push the current in the downward direction. I hope you understand. Okay. So if we are saying that, then the net voltage, what is actually being applied to the circuit, because these two are connected in anti-series, it is only 24 volts now. If I try to look at it, 32 minus 8, 24. I can say it that way. Or if I have to write the Kirchhoff's voltage equation or mesh voltage equation, I can write this as 32 minus 8 is the current, is the total voltage that is being applied, and I can say the total resistance is 20 plus 2 plus 8, right? So this is 22 plus 8, 30 ohms. So I should say 20 plus 8 plus 2 multiplied by say I1, if I am calling this as I1. Please note the direction. The direction is upward as far as this current
Ma'am,
is
you are
concerned.
applying KVL law.
Yeah,
Are you applying KVL law?
exactly. I'm just applying KVL. There is only one loop, nothing more than that. So I can say total resistance available is 30 ohm and the current that is flowing is I1, which will flow in this direction because this voltage will dominate over this voltage because this is smaller. So I'm going to have 24 divided by 30 is equal to I1. Okay. So if this is the current, how much is it? So I'm going to have 0.8 amperes. That is going to be the current. The current that is flowing is 0.8 ampere. Now, how much is the voltage across this? That is the open circuit voltage across VAB. So I can either calculate it like this. 8 plus 2 is 10. 10 multiplied by 0.8 ampere is 8 volts. So 8 volts plus 8 volts, I'm going to get 16 volts across this. Am I right? Because this 8 volts will be added to the current is flowing in this way. So I will have plus minus here, and this plus minus is also additive. So 8 volts is totally dropped across these two resistances and 8 volts is here. So 8 plus 8, 16 volts. Is this clear? So I'm going to have VAB as 16 volts. This is the open circuit voltage. This is going to
Ma'am,
be
can you
the,
please repeat this?
yeah. The current is 0.8 ampere. Do you understand that?
Yes,
The
ma'am.
current is 0.8 ampere. Do you understand that?
Yes.
Okay. So if I say that the current is 0.8 ampere, I am looking at the voltage of point A with respect to point B. So point B is same as this point as well. And if I try to look at the entire path, there is a voltage rise of 8 volts here because of the battery. The current is flowing in this direction. So I will have plus here, minus here, plus here, minus here. The total resistance here is 8 plus 2, which is 10 ohm. And 10 multiplied by 0.8, that is going to be 8 volts. And 8 volts is again voltage rise in this direction. I have minus here, plus here, minus here, plus here. So 8 plus 8, these two have to be added, that is 16 volts. Okay, either I can do it this way or another way is, if I assume that the current is flowing in this way, I'm going to have plus here and minus here. I can write it this way too. And 20 multiplied by 8, I'm going to have 16 volts drop across 20 ohms as well. And it is voltage drop. This is plus and this is minus. The voltage that is applied here with the battery is 32 and there is a voltage drop of 16 volts. So 32 minus 16, that is has to be 16. So either way you will get 16 volts as the open circuit voltage across AB. Okay, so open circuit voltage across AB is going to be 16 volts. So this is the Thevenin's voltage what I am getting. If I am asked to draw the Thevenin's equivalent circuit as per the terminals A and B, I am getting an open circuit voltage of 16 volts. The next one that I need to do is I have to get what is RT. I have to short circuit this A and B terminal and find out how much is the current through this terminal. Okay, so how do I find the current through this terminal? That is the question next. So let me again redraw the circuit. Okay, let me try to redraw the circuit. So I'm going to have 8 volts here and this was 8 ohm. And after that, I think we had 2 ohm and I had 20 ohm and this was 32 volts, and I am short circuiting this completely. So how do you find the current? Tell me now, how are you going to find the current through this? If you calculate what is, let us say I1 here, and let's say you calculate I2 here. If I say this is I, this will be the summation of those two. Can you not calculate it that way?
Yes, ma'am.
Right?
Can you repeat again?
If I just calculate this current, which is I1, I calculate this current, which is I2. Kirchhoff's law tells me that I equal to I1 plus I2. Can you not calculate it that way? That is what is ISC, right? So I'm going to have this as 0.8 ampere. Am I right? This will flow as 0.8 ampere. And this will flow as 32 divided by 20. That is 1.6 ampere. Am I correct? So this is going to be totally 2.4 ampere. Right? So ISC is going to be 2.4 ampere. Okay? So I can calculate RTH to be VTH divided by ISC. Okay? So in this particular case, this is going to be 16 volts divided by 2.4 ampere. So you can calculate how much is it? How much is it? 4 4s are 16, and I'm going to have 6 4s are 24. So 4 by 0.6, right? Is that so? Okay, fine.
6.66, ma'am.
6.66. So this is going to be 6.66. So I can represent this entire network, what I have got here, by simply having a VTH of 16 volts, and I'm going to have a resistance of 6.66 ohm. This is especially useful if, let us say, I have two terminals in my circuit where I'm going to connect different types of loads. Maybe I will connect a 60 watt bulb. Maybe I want to connect some kind of computer or something else, some other load, and I want to analyze the circuit for different types of resistances, different types of loads that are connected across these two terminals, and I want to see how the circuit is performing. To do the calculation repeatedly with different types of resistances, it is going to be really, really difficult for me. Rather than that, if I have the Thevenin equivalent, all I need to do is I am going to connect the load here, simply whatever be my load. And then I can simply find out how much is the current that is being drawn, how much is the kind of power that is being imparted to the load. All those things, it will be very, very easy for me to analyze when especially I'm talking about different types of loads being connected to the same terminal, right? I should be able to analyze it with ease. That can be done very easily with Thevenin's equivalent circuit. This is extremely important from the power grid point of view, because if you look at it, a generating station, it may have so much of voltage generated, so much of power generated, and it is going to various load centers, maybe to your residential complex, to another commercial complex, to another industrial complex. So if I know exactly what is the input side, that is, what is the kind of input side circuit which can be represented by a Thevenin's equivalent with a particular voltage source and with a particular impedance, then I can say for different variable load conditions of my residential complex or of my commercial complex, how the power distribution system behaves. I will be able to predict this quite easily. Okay, so that is where the Thevenin's equivalent circuit comes in really, really handy. If it is a small circuit like this, what we had done, it doesn't really matter too much. But when we are looking at the overall behavior of the circuit, especially in a complex network with variable load, it becomes extremely important. Now, rather than Thevenin circuit, if I want to represent this by Norton's equivalent circuit, this is the Thevenin's equivalent circuit. If I want to represent this by Norton's equivalent circuit, I should be able to simply say that 16 divided by 6.6, which happened to be 2.4 ampere. So I can represent this by 2.4 ampere current source, which is connected in parallel with the 6.66 ohm. And this is the terminal A and B. So this is terminal A and B in the case of Thevenin's, and this is the terminal A and B in the case of Norton. So the Thevenin's and Norton's equivalent circuit are two sides of the same coin. In one case, you are representing it by a current source. In the other case, you are representing this by a voltage source. And in one case, you are representing the resistance in series form. In the other case, you are representing it by the current form. The parallel form. That's all is the difference. One last point before I conclude on Thevenin's. Here I told you that R Thevenin's can be calculated as V Thevenin by ISC. This is a generalized procedure we adopt for any kind of circuit that we are working on. In this particular circuit, all these voltage sources are independent sources. They are not dependent on any other circuit parameter. If it is a 8 volts battery, it will always deliver 8 volts. And if it is a 32 volts battery, it will always deliver 32 volts. Nothing less or nothing more. So these are kind of set in stone. We are not going to be able to modify the values at all. They are all constant values, fairly constant values. So whenever we have these kinds of independent sources, we should be able to get RTH in a simpler manner. In this particular case, for example, I basically had a 8 volts battery. I had 8 ohm resistance. I had 2 ohm resistance here. Then we had a 20 ohm resistance and we had a 32 volts battery. And this was the terminal A and this was terminal B. This is what we did in our circuit. Now, if I want to find out RTH in a simpler manner, what I can do is I can just see from this side, the circuit, nullifying all the voltage and current sources, which are independent sources. So I can nullify the voltage source by short circuiting it. I can nullify this voltage source by short circuiting it. So now my network becomes, this is 10 ohm and this is 20 ohm. Okay. And here is my terminal A and this is going to be terminal B. And I'm going to visualize the circuit from this side and see what is the equivalent resistance. It is 10 multiplied by 20 divided by 10 plus 20. Right? So this is going to be 200 divided by 30. Hopefully this should work out to again 6.66 ohms. So whenever I have independent voltage sources and independent current sources, I do not have to go through with calculating the short circuit current. It is not essential for me to calculate the short circuit current. Rather than that, I can directly calculate what is RTA. Okay, so before we conclude on Thevenin's and Norton's theorem, the last one we are going to look at it is a circuit with dependent sources. We are going to solve the Thevenin equivalent for this circuit with, so find Thevenin's equivalent across AB for the following circuit. Okay, so let me draw this circuit. The circuit is somewhat like this. I am going to have one 6 ohm resistance, then a 2 ohm resistance, which is in series with this, and there is a 5 ohm resistance, which is coming up here. And there is a current source, which is, I should draw this as a dependent current source. So I'm going to draw it like a dependent current source. So this is 2I, where I is the current through the 6 ohm resistance. Now from here, I have a 4 ohm resistance and a 6 volt source. Okay, and what we are being asked is to find the Thevenin's equivalent across A and B. Okay, so this is what is being asked, and whenever you have a dependent source, never ever try to calculate RTH by short circuiting the voltage sources and open circuiting the current source. So RTH should be found out only as VOC divided by ISC across AB. You should never do it directly by calculating like what we did at the end in the last page, last slide. Okay, so this is the circuit and this is a dependent source. This is going to be the dependent source. So this is a dependent current source. Okay, so let us try to first of all find out what is the voltage here between A and B. What is VOC? We'll try to find out. So how do we go about doing this? So if we want to really do this, we can use, it is open circuit. So please remember this is open circuit voltage. So we have only 2 meshes. So let me probably redraw this a little bit in a more straightforward manner. After all, I'm going to have 4 and 6, both of them now in series because this is open circuited. So I'm going to have 6 volts. So let me draw this entire thing once again. This is 4 ohm. This is 6 volts. This is plus and this is minus. This is going to be 6 volts. And I'm going to have 6 ohms here. Please remember this is I. I have to write this as I. And then I'm going to have a 2 ohm here. This is one mesh. The other mesh I'm going to have is, this is 5 ohm. And I'm going to have a current source here, which is 2I. And I'm going to have this as the complete circuit. Now this point is B and this point is A. So I want to know the voltage across this terminal. That's what it is. Now I can assume, yeah. So I can assume this as, let us say, I1 and this probably as I2. So I1 and I2 are opposing each other as far as the 2 ohm resistance is concerned. So let me try to first of all write the
How did you
equations.
come to know the direction of current?
What?
How did you come to know the direction of
I am
your
just
project?
assuming. You can assume it other way also. I have just assumed I2 in a particular direction such that it coincides with this. That's all. I can always assume it the other way around also. Even I1, I can assume it the other way around. There is nothing wrong. I am just assuming it this way. So only thing, when you write the equations, be consistent with the direction of current you are assuming. Okay. So in this particular case, the current is flowing out of 6 volt source. So I can write in this for mesh 1, I should be able to write the equation as 4 plus 6 plus 2. All of them are carrying the current which is I1. So 4 plus 6, 10, 10 plus 2, 12. So I should say 12 times I1, and 6 is not carrying any other current other than only I1. And 2 is carrying the current which is corresponding to I1 as well as I2, right? So I'm going to write that as minus 2I2 equal to 6 volts. Okay, this is what is my first mesh 1 equation. And please note the current through 6 ohm resistance decides what is the value of the current source magnitude. The current source magnitude is given as 2I. So this is 2I, which means in this particular case, I is same as I1. There is no other current that is flowing through 6 ohm. So I can say this current source magnitude is 2 times I1 itself. Nothing more than that. So for mesh 2, I should be able to write the equation. Let me try to write the equation. In fact, I can simply write 2I should be equal to 2 times I1, which is also instantly equal to I2. Am I right? Because there is no other current that is flowing through this current source, this branch. So this is 2I, which is incidentally equal to I2 itself. So I'm going to have I2, which is also equal to 2I, which is 2I1 itself. So this equation becomes pretty simple in terms of substituting 12I1. I can write 2I1 is equal to I2. So this becomes 4I1, which is equal to 6 volts. Yes?
Ma'am, in mesh 2, you didn't write a 5I2, right?
I don't have to write that at all. Please remember, this is a current source. The current is flowing, which is 2I. The current source need not be multiplied with 5 ohm because I'm only writing a current equation here, not even a voltage equation. I have only got one current source, which is 2I. And that 2I is not, this branch is not carrying any other current. There is no resistance, nothing. So this 2I should be equal to whatever is the mesh current. Mesh current is I2. And this 2I is same as what is the current that is flowing through the 6 ohm resistance. And that is small I itself. And that is same as I1. There is no other current flowing through 6 ohm resistance. That is the reason why I am able to write simply 2I, and I is after all equal to I1. So I can write 2I is same as 2I1, which is also incidentally equal to I2. Okay. So I am not writing KVL equation here. No doubt. I am only writing simply current equivalence. That's all. When I have a dependent current source, I have to think as to how I would be able to zero in on the value of the dependent current source. How can I get that? So in this particular case, I'm going to have 8I1 equal to 6 volts, which means I1 is equal to 6 divided by 8, which is 0.75 ampere. Right? If this is 0.75 ampere, I'll have to calculate how much is I2. I2 we said is 2 times I1. So this current is going to be 1.5 ampere because twice this value. Note the direction. This is 1.5 ampere. So what I need to do is, I need to look at this. If the current is flowing in this direction in 5 ohm, this is plus and this is minus. And if the current is flowing in this direction in 6 ohm, this is plus and this is minus. So if I try to look at it from B, whatever is the voltage drop that is happening in 5 ohm and whatever is the voltage drop that is happening in 6 ohms, if I add both of them, that will give me VAB. So VAB, which is the open circuit voltage, that will be given by voltage drop in 6 ohm plus voltage drop in 5 ohm. Both of them have to be added. Voltage drop in 6 ohm is how much? That is essentially 6 multiplied by 0.75. And voltage drop in 5 ohm is 5 multiplied by 1.5, because that is 1.5 ampere. So I'm going to have 7.5 volts plus, how much is this? 4.5. So this is going to be 4.5. So 4.5 plus 7.5, which is 12 volts. So my VTH is going to be 12 volts. Okay. Now I have to find the short circuit current. I should not be doing this by nullifying the voltage source and nullifying the current source, because this is a dependent current source. I cannot nullify this. So I have to definitely take a little, not shortcut, I have to go through the complete long way. So let me again redraw the circuit for finding.
Mama still didn't understand the mesh 2 equation. Mama still didn't get how did you write the mesh 2 equation.
We have not written the KVL. All we have looked at is whether we are able to express this current in terms of anything else, which is a known quantity. That's all we have done. We have not really written the mesh equation. Yeah. Yeah.
But how can we write? Write 2I1 is equal to I2?
This is 2I. This is given already. This, what is given here is 2I. And what is I? I is the current through the 6 ohm resistance. And what is the current through the 6 ohm resistance here? That's same as I1. There is nothing else, right? Am I right?
Yes, ma'am.
Yes. Yeah, so I should be able to write 2I1 equal to I2, which is same as the current source. If I just don't have any other current flowing through this terminal, that is same as I2, which is the current source value itself, which is 2I, isn't it? Isn't it?
Yes, ma'am.
Right? So, see, this you would get by practice. Now for finding the short circuit current, I'm going to draw the circuit and leave it at that because I think we won't have time. So let me draw the circuit corresponding to this. So I'm going to have basically, what happened? So I'm going to have 4 ohm, 6 volts. Then I'm going to have the 2I here underneath. This is 2I. Then I'm going to have the 6 ohm, which is connected here. This is I. So this is what is going to determine what is the current value here. And I'm going to have the 2 ohms here. Then I have 5 ohm here. Right? Now this is A and this is B. If I want the short circuit current between these two, all I need to do is just short circuit. So what I need is this short circuit current. So in this particular case, if I have to write the equation again, please note there are three meshes. So I might call this as I1, for example. I might call this as, say, I2, and I might call this as I3. First thing I want you to notice is I2 is same as 2I. There is no difference between the two because I2 is flowing through this particular branch which is same as 2I. So I2 is 2I. There is no doubt about that, right? Whereas if I look at 6 ohm resistance, current through 6 ohm resistance, which is actually we are specifying as I. This is I. This is the current which is I. Okay. So that is going to be equal to, please note I1 is flowing in this direction whereas I3 is flowing in the other direction. So I have to have I1 minus I3. Is this clear? I1 is flowing in the direction which is from left to right, whereas I3 is flowing in the direction which is right to left. So I1 minus I3 is going to be the current in 6 ohm resistance, which is I, which is determining this value. Okay. One more thing I need to specify is the short circuit current is same as I3. So I should say I3 equal to ISC. So if I solve for I3, that is good enough for me. Okay. So let me try to write the equations quickly and then we will you will calculate rest of the stuff. So for mesh 1, I can write the equation as 4 plus 6 plus 2. So 12. So 12 times I1 and minus 6 times I3 and minus 2 times I2 is going to be equal to 6 volts. This is mesh 1 equation. Okay. And if I have to write this equation for mesh 2, again, I don't have to write the complete voltage equation. I can simply write this as 2I is the current, which is actually same as I2, which we had already written, which is going to be I1 minus I3 multiplied by 2. This we had already written. I is equal to I1 minus I3. So I should be able to write this. And if I want to write for mesh 3, I can write 6 plus 5, 11. So 11 I3 and 6 is carrying I1 also. So that will be minus 6 I1 and minus 5 I2. Plus 11 I3 equal to 0. That's it. So this is the mesh 3 equation. So you should be able to use even mesh 1 and mesh 3 ultimately to arrive at probably your solution for, I3, which is the short circuit current. So please try to work this out. We'll continue with this in the next class. Okay, fine.
Ma'am, is it 2 I1 minus I3 or I2?
Just a second. Let me probably just, yeah. 2 I1 minus I3. 2 multiplied by I1 minus I3. Please remember I1 direction we have taken this way. And it is already given I has to be taken in this direction. So 2I will be 2 multiplied by I1 minus I3. I3 is in the opposite sense. Okay? Is that clear? I1 is in this direction, whereas I3 is in the opposite direction. Okay?
Yes, ma'am.